everyone, and a warm welcome to this online training program which is being planned on seawater desalination, a reliable and sustainable solution to alleviate domestic and industrial water scarcity. I'm glad to see so many participants joining us for this program. Water Digest, we have been doing a series of webinars and other training programs, and today we are glad to invite you and to have you for this special program which is being planned on important topic, the desalination. As we know that the entire world is facing the water scarcity, and India is no exception to that. And there are so many technological interventions and innovations, and desalination is one such innovation which is giving us a positive hope. And to talk about it, we have an expert of the segment with us. We have Mr. K. Syed Amir Basha, who is the CTO from VATech Wabag with us. Mr. Amir brings along the experience in the same segment, say more than 3 decades. And he had been serving earlier in the Middle East, and now he is in India. And then he brings along, as I said, an experience of more than 3 decades. I hope he'll be able to answer your queries and to bring a lot of knowledge along on this particular topic. Also, I would like to introduce you with the format for today's webinar. We have a format wherein we will be having a presentation and the technical session of 1 hour 45 minutes. Post that, we'll open for 15 minutes Q&A. Right on front of your screen, you can see there is a window where there is an option of writing your chat. You can write down your queries, you can share it with us, and we will try to answer your queries as many as possible in the given time frame. If not, you may please write to us, and we will definitely take it forward to our email communication. So I hope you'll find this overall program enriching, informative, and interesting. And once again, without delaying further, once again, welcome all of you and our honorable trainer, Mr. Amir, who will take this forward now. Amir, over to you.
Very good morning to all. The topic for the presentation is Seawater Desalination, a reliable and sustainable solution. This has been proven in all other Middle East countries and Western countries. Still, it is to take a big leap in India, but this has been already proven. I will try to explain you the various steps we involved in making it proven. The content which I'm going to present here is one, need for desalination. What are the driving factors which are driving desalination, especially in India? Present major desalination technologies. Where does India stand in desalination currently? Organizations like WABAG role in desalination developments. Future desalination technologies which are under development. Factors influencing desalinated water cost. The myth about desalination and the clarification to it. And finally, how industries can source the raw water for desalination. In this slide, you can see that around 600 million people are facing in this world scarcity of water, and which is going to be increased to 2.7 to 3.2 billion in 2025. You can see in 2025, India is totally going to be under water stress. This is the current scary picture of India's water stress. You can see that water stress is totally there. There is some arid zone which are marked in maroon color, and high areas of stress are in red and orange, and very low is in pale orange color. So more than 200 million people did not have access to safe drinking water by 2017 itself, which is now around 300 millions. And the picture shows the water stress in India in the current situation, that is 2020. Factors driving the world towards the seawater desalination are limited freshwater resources because it is dwindling due to occupation and sharing with others, increasing contamination of freshwater sources due to pollutions, increasing population which is also consuming more water, migration of people to urban area causing a lot of demand in the major cities, disputes on ownership of source water. For example, a dispute between India and Pakistan or Mexico and USA regarding the water distribution from the rivers is also increasing the need for desalination. Higher disposable income of the people in developing economies, they are afford to pay more for the water even if good water is available at a higher price. So this is also driving desalination. High rate of industrial growth also increases the demand for the desalinated water. The main factor that is driving the world towards seawater desalination is desalinated water costs going down continuously. In 1980, if you see, the water cost was around $3.2 per meter cube. That is, 1,000 liters was costing around 3.2 US dollars, and it has come down gradually. But recent tender documents which are floated by Saudi water company SWPC had brought down the water cost to $0.41 per meter cube. That is, it 3 paise per liter of water. Previously, 6 months back, another tender was there where the price was 0.47 US dollars per meter cube. This is for Yanbu 4 plant. But Jubail 3A plant for 600,000 meter cube per day capacity, the water cost has come down to 3 paise per liter. So this is the one which is making more desalination a more attractive solution. About 50% of world population live around the cities close to the coastline, so sea is easily accessible. And you know, ocean is sustainable raw water source. About 71% of the earth's surface is water covered, and the ocean holds 96.5% of the earth's water. So this non-diminishing resource makes us easily accessible for desalinated water. Tightening of regulation of groundwater extraction for industries are also driving the desalination. People in all continents have already accepted this water for drinking application and utility applications. Desalination is now a mature technology that can supply desired quality of water reliably and at affordable price. Desired quality of water means I, with the desalination plants, we can even develop water very close to 2 microsiemens per centimeter, or you can produce utility water meeting whose requirement. So the technology is now flexible, and we can have a desired quality of water, especially with respect to seawater reverse osmosis. Multiple modular units can be added in stages in order to improve the water quality. Present major desalination technologies related to salinity of feed water are shown here. With the lowest feed water quality, you can go for ion exchange or electrodialysis process. Then there is a brackish water RO, which is similar to the RO units which are used in kitchen. And there are seawater reverse osmosis plants which are designed for a TDS of water between 10,000 to 50,000. There is a limitation in the seawater reverse osmosis system because more than 50,000, the pressure required is increasing above 85 bar. So the membranes are not available except one of the manufacturer which is designing membranes up to 100 bars pressure, and they are used in the brine water conversions. And the last is the distillation system, which is suitable for even higher TDS of water, and this was most commonly used technology even 40-50 years back. But after the invention of membranes and making it more competitive, the desalination technology with seawater reverse osmosis is taking over the thermal process. The most popular process in seawater desalination are MSF process, which is multi-stage flash desalination. The second one is multi-effect desalination process, and third is the seawater reverse osmosis desalination process. They are shortly called as MSF, MED, and SWRO. And for brackish water plant, which is well water or water with a low TDS, brackish water reverse osmosis or electrodialysis process were very commonly used once. You can see any desalination plant has 5 major systems in it. One is intake system. The function of the intake system is to bring the water from the source up to the desalination plant. The second one is the pretreatment system. The function is to make this raw water suitable to be admitted into the RO system or any desalination system. The pretreatment system assumes more importance in case of reverse osmosis plant because membranes have pores which are very, very small, like 0.001 microns. So any particles going can block, like even bacteria can block, viruses can block the pores, or it can also biofouling can happen, also scaling can happen. So the pre-treatment system assumes more importance in case of a seawater reverse osmosis plant. The thermal plants are more rugged plants and they can handle with a less efficient pre-treatment system. Also, the pre-treatment system is important when the water quality is very bad. When the water quality is bad, the pre-treatment has to do extra effort work in order to remove all the impurities and make it suitable to be admitted into the RO plant, meeting the requirements of membrane suppliers. So pre-treatment, there are different type of pre-treatment system available. One is dual media filters. The second one is lamella clarifiers. The third one is dissolved air flotation system, and then rapid sand filters. So these are some of the examples which are used. So the choosing of the right desalination technology depends on the water quality, raw water quality, what we receive from the source. The third important system is the heart of the system, which is called desalination system. In reverse osmosis system, it is a membrane system with a high pressure pumps and energy recovery devices. Whereas in case of a thermal desalination plant, it is a thermal desalination system which with its own dosing system for anti-scaling and anti-foaming effects. The fourth system is the outfall system, which is also very important in case of environmental issues. See, the brine that is coming out of a desalination plant has slightly higher salinity in case of thermal plant, and it also has a slight temperature effect. Whereas in reverse osmosis, the salinity level is slightly higher because we go in for higher recovery. The salts that are rejected due to the production of a low salinity water is carried by the rest of the water and it is disposed into the sea. So the modern techniques use diffusers with the multiple nozzles, which has a special recirculation arrangement to diffuse the water and dilute it within a short radius. Say the radius is around 30 to 40 meters. And this is very important because we take the brine deeper into the sea. In case of in India, we are taking it around 800 to 500 meters, and in countries like Australia, where environmental requirements are very stringent, they go up to a depth of around 15 to 20 meters, and to a sea from the seashore up to 3 kilometers distance in order to dispose the seawater. The fifth system, which is also equally important, is the post-treatment system or a remineralization system. Because in thermal desalination plant, the quality of water that is coming out will be around 5 milligrams per liter TDS. And so this water will be very much acidic in nature, that is less than 7 pH. Even in seawater reverse osmosis system, the water quality what we get will be slightly acidic. So in order to make it to suitable pH at around 8 to 8.5 for the utility applications, we have to do some calcium dosing and CO2 addition to in order to increase the solubility of lime in it. So the post-treatment system also has the facility to add any other chemicals, like in some of the countries they add even fluoride to increase the in the form of a calcium fluoride to increase the fluoride content in the water. You can also add some flavor to the water even by adding some additives. So the post treatment can do these functions. So these are the major 5 systems applicable for any desalination plants. So the SWRO shown here can be replaced by any other desalination technology. Multi-stage flash process. The salient feature of this process is the production of vapor in this process is by means of flashing the seawater into evaporator zones, which are maintained at low pressure. So when water at a particular temperature, say from 90 to 110 degrees, when it is taken into an evaporator and it is allowed to flash at a lower pressure, so that vacuum is in that vacuum the vapor that is generated is taken up and then it is condensed. This repeated flashing occurs in multiple stages by maintaining the succeeding stages at a lower pressure than the preceding stages. That means the first stage will, if it has a pressure of X, the pressure next in the stage will be X minus something, and there are around modern plants having up to 35 to 36 stages, and more the number of stages, the efficiency or GO, or we call gain output ratio, is very high, or specific heat consumption also comes down. The water vapor that is generated is condensed by the water that is passing through the tubes, and in the process the water that is seawater that is passing through the tubes gets also heated. I'll explain in the next slide the flow diagram. And this type of MSF plants are very common for dual purpose application, where it is electricity is generated, and the waste heat that is generated in the which was previously rejected in the condenser, instead of condenser it is taken to the evaporators of the desal units and heat is rejected there. The condensate is brought back to the boilers, and the heat that is used for desalination purpose. So it is like a dual plant using the waste heat generated from the power plant. It is commercially competitive for large size plants, and to say that the biggest desalination plant which is already commissioned in Saudi Arabia is 1 million meter cube per day plant, which has a capacity of 700,000 meter cube per day of MSF desalination, and 300,000 of reverse osmosis system. Because the waste heat available is sufficient only to generate 700,000. So MSF unit of 700,000 capacity, 700,000 meter cube per day capacity is installed. And this type of plants with the 2 different technologies are called hybrid desalination plant. It is a very matured technology which is existing for more than 100 years, and the process is well developed process, and this requires only a simple pre-treatment system. We can see that this is a flow diagram of a typical simple flow diagram of a MSF plant. First, let us take the condenser. The feed water from the sea is pumped through the feed water pump. You can see in the green lines, and it is taken through the tubes, which cools the vapor and condenses the vapor into water, and that water is called distillate, and it is taken out. The water that is heated is taken up, and part of this water is drawn as a makeup water, and most of the water is returned back to the sea. This is shown in the green colored portion. The makeup water mixes with the brine that is recirculated, and it passes through various stages in the heating coils. These coils, in the process of cooling the vapors generated in different stages, produces vapor, condenses the vapor, and in the process, the water gets heated. So in each stage, it gains around 2 to 3 degrees centigrade, and it finally reaches the brine heater, where it is finally heated by the steam that is coming down from the thermal plant, or standalone desalination plant. It is supplied by means of a boiler. So the steam that is coming out heats the water to a temperature, we call it as a top brine temperature. It is in the range of 90 to 110 degrees normally, and in some plants we have gone up to 135 degrees also. The steam that is condensed is collected, and then it is returned back to the boiler for further processing. It is a closed loop arrangement. The water that is heated enters the first stage of evaporator, which is maintained at vacuum, and it flashes. The vapor that is generated goes up, and then it is cooled by the heating coils that is bringing the seawater, and then the condensed vapor, which is a distillate, is sent to the last stage. The same process repeats. So the flashing takes place in adjacent downstream evaporators by maintaining those evaporator stages at a slightly lower pressure than the preceding stages. In order to increase the recovery of the system, only part of the brine that is coming out is blown out, and remaining is recirculated back into the system. Since the flashing takes place, vapor generated in each stage, the concentration of the seawater flowing down from one evaporator to next evaporator gradually increases, and finally reaches a highest area in the condenser area. So from there, the brine discharge and recirculation takes place. This shows a Ras Al Khair plant, which is a 1 million meter cube plant, which I told, where the MSF process generates 700,000 meter cube per day of water. It is in Saudi Arabia. The next technology is multi-effect desalination process. The salient process here is, in contrast to MSF process, where flashing generates the vapor, here film boiling generates the vapor that is required for the desalination. And if you see MED plants, the number of stages are less when compared to MSF plant. Generally, it has got 6 to 8 stages in the modern high capacity plants. There were initial plants which were having only 2 stages or 3 stages, where the efficiency of conversion is much lesser, and the GOR and the specific heat consumption was slightly higher. The more the stages, the efficiency of the plant is better. Actually, the vapor that is generated is condensed inside the tube by spray of water that is coming out, and cooling the seawater, cooled by seawater that is sprayed outside the tubes. And This process is gaining more important because the price wise, as well as the total cost wise, as well as the efficiency wise is slightly better because of the number of stages being low, and in small capacities up to 400,000, it is replacing gradually the MSF process. It is also similar to MSF process used in the dual purpose plant, where the waste heat from the power boilers or extraction steam power from the power boilers are used for the supplying the heat for the brine heater, or to heat the seawater that is entering the system. This is also commercially competitive for small capacity, but even though we call small capacity, nowadays the MED process are available for 350 to 400,000 meter cube per day units, and it also requires only a simple pre-treatment process. The next slide will see the MED TVC, thermal vapor compression flow diagram. Here the steam enters and then creates the vacuum that is required for the you can see that for the whole process the vacuum is required, and vacuum is generated by means of an ejector system. So the steam passes through the ejector, and then after that the process, it enters into the first evaporator stage, where it passes through the tubes. You can see the steam is coming out, entering in as a red, and then turning into orange, and then entering into the tubes. So the vapor that is going inside is cooled by means of the water that is sprayed into the stage, the seawater that is sprayed. And during the process, it cools the vapor and then condenses. This water is the water that is condensed is from the steam in the first stage is high purity water, and it can be returned back to the boilers for the process. And during the process of this evaporation, film boiling takes place over the tube surfaces, and the vapor is generated. The vapor generated goes to the next stage. The vapor generated is shown in the red arrows, and it flows to the next stage. And in the next stage, this vapor flows through the tubes, and water is sprayed externally to the tubes, and in the process a new vapor is generated and goes to the next stage, and the vapor that is flowing inside the tube gets condensed and then gets collected. The condensed water is collected and taken to the last stage as a distillate, and the water that is sprayed is collected in the bottom also is taken to the last stage. Part of the water is recirculated as the water that is for the process, and remaining is blown down completely. So you can see that this is the last stage in which the seawater that enters cools the vapor in the condenser zone. Part of this water is taken as a makeup water, and the remaining is returned back to sea completely. So in a simple plant, the brine completely it is blown down. In other bigger size plant, this brine is taken and mixed along with the makeup water, and it is sent to the different stages for spraying through nozzle jets. This is a picture of a MED process which is there in Abu Dhabi. There are 12 units of 38,640 meter cube per day units here. The most commonly used process, which is gaining more and more important in the recent time, is seawater reverse osmosis process. This is the cheapest desalination process for any standalone desalination plants. In MSF and MED process, if you convert the heat energy that is supplied into electrical energy, the power consumption will be very, very high in the range of around 38 kilowatt hour to 40 kilowatt hour per meter cube. But in seawater reverse osmosis plant, the process now the specific power consumption has been brought down close to 3 to 3.2 kilowatt hour per meter cube, and depending upon the simplicity of the process. It's a cold process. Seawater reverse osmosis is a cold process, and uses the pressure energy for desalination through reverse osmosis. This is very commercially competitive for all size of plants because it's can be modular and it can be added on to the existing ones to increase the capacity. It is also quick start and quick shutdown process because in thermal process you have to generate the vacuum, so you have to allow the water steam to pass through the ejector or water to pass through the ejector and create the vacuum that is required in the system. And it takes and also the heating rate and cooling rate in the boilers and other things are limited. That restricts the startup and a slow startup timing and a slow shutdown time of a thermal desalination system. And whereas in a reverse osmosis plant, the plant can be started within 15 minutes. An individual RO unit can reach full capacity easily, and shutdown can be also done instantaneously just by a trip and can be flushed and then made ready for the next startup operation. So it is very suitable for quick startup and shutdown application. It's also a mature technology. It is there for more than 30 years. It has developed, and now it is almost come to a saturation. There are different other technologies are being developed in order to have more efficiency, more less specific power consumption. And in the following, in the slides which are to follow, you will see that how the technology has taken over the thermal process. But this technology calls for a well-designed pretreatment system, as I explained, because of the fine pore size available in the membranes and because of the high recovery in this plant when compared to thermal plants. We go in for 40 to 50% recovery. Because of that, the scaling potential is also high that needs a pretreatment to be done properly. Development of high energy devices, variable frequency drives usage, and low pressure membranes has made this process a very competitive process. Most of you will know what is osmosis and what is reverse osmosis. Just to touch upon osmosis, if you have a semi-permeable membrane on one side and you have fresh water and the other side you have salt water, the water molecules in the fresh water will pass through and try to dilute the salt water, and due to the salt concentration difference, and because of this the water level will rise, and the other area the water level will go down because the part of the water molecules has passed through this area. When the water level reaches a certain height, the process reaches an equilibrium where exchange of water takes place and salt takes place, and equilibrium is reached, and that is the stage. The level difference is called osmotic pressure. And this osmotic pressure, only when you overcome this in a reverse osmosis process, you can produce fresh water to pass through the semi-permeable membrane, water molecules to pass through some semi-permeable membrane and produce fresh water. So in osmotic process, you due to the concentration difference, the real water molecules pass through the semi-permeable membrane and dilute the salt water. In reverse osmosis, you apply a pressure which is much higher than the osmotic pressure to force the water molecules to pass through the pores in the semi-permeable membrane and reach other side to produce low salinity water, which is pictorially explained here. You can see in a RO process, monovalent, divalent, and trivalent ions, mostly 99% of them are rejected, and only 1% maximum, not even 1%, even less than that, 0.6 to 0.7% only is allowed to pass through. You can see only the water molecules pass through the pore sizes and come to the other side to generate low salinity water. And also in the process, you can see virus, bacteria, suspended particles, silt, everything settles down on the membranes and try to clog. And this needs to be cleaned by periodically cleaning the RO membranes. This is a simple flow diagram of a seawater reverse osmosis system. Seawater is taken into the feed tank, then it is pumped through a feed pump, passed through a multimedia filter. This multimedia filter is a pretreatment segment which can be replaced, and if the quality of feed water received is bad, which has got more suspended particles, then we go in for lamella clarifier. If it has got algae or some amount of oil or TOC level is slightly higher, we prefer to use dissolved air flotation system. But if it is a water with the allowable range, acceptable range of suspended particles, then we slightly go in for a multimedia filter. But the recent times, the multimedia filter is getting also partially replaced in some of the sophisticated plants with ultrafiltration system or microfiltration system, which is a membrane-based pre-treatment system with once again having pores which are 0.05 or less. Because of this, efficiently the suspended particles are removed, and with that system you can go in for slightly higher recovery in the RO plant, because the quality of feed water that is received from these membrane filtration system is much superior to multimedia filters and lamella clarifiers. So water after passing through multimedia filter is passed through a guard filter. This is cartridge filter of 5 micron size, and this is to prevent any particles going into the RO membranes from multimedia filter, because multimedia filters generally have a backwash system, and sometimes what happens, the media is carried over and it is brought into the cartridge filter areas, and cartridge filter prevents them going into the RO modules. So generally, in a UF plant, which is with the inline system, we don't have cartridge filters, but we generally provide this cartridge filter when there is a break tank or when DMF water is directly sent to RO modules. So after the guard filter, the water is pressurized and sent into the RO modules directly. The pressure ranges from 50 bar to 70 bar depending upon the salinity of the water. And so the higher the salinity, the pressure is higher. So in order to save the energy consumption in RO module, the brine that is coming out of the RO module, which is still retaining the entire pressure, is passed through a pressure exchanger, and part of the seawater is before admitting into the pump, high pressure pump, it is taken through a pressure exchanger and booster pump, and when it is brought here, the pressure is same as that of high pressure pump pressure and discharge pressure, and the water is admitted. For example, if the recovery of a plant is 40%, 40% of seawater is allowed to pass through a high pressure pump and taken directly to the RO module. 60% of the water is passed through a pressure exchanger, which extracts the energy from the brine, and the remaining energy, the difference between the discharge pressure of high pressure pump and the pressure exchanger discharge, is added by this booster pump, so that the pressure at this point of joining between high pressure pump and booster pump is maintained same, and then it is sent. So 40% of water only is pressurized through a high pressure pump, and the 60% of water is boosted by around 2 to 3 bar pressure. So there is a saving of energy in boosting the pressure of 60% of the water. That makes the specific power consumption very, very low. And after passing through the module, the low TDS water coming out is taken and taken for and forwarded to remineralization system, and the brine, after passing through pressure exchanger and losing all its energy, is sent to the reject water system. RO modules during the process of operation will get either fouled or scaled. Mostly fouling is common, scaling is very, very little. Only in the brackish water plants we see more scaling potential is there. In seawater application, unless the recovery is very high, the scaling potential is very low. So there is a CIP system, that is cleaning in process system, is provided in order to clean the membranes. So there are two types of cleaning that are used generally. We call as high pH cleaning and low pH cleaning. In order to clean the membranes, rejuvenate it, and make it ready for next cycle of operation. The cleaning cycle is generally it is 2 to 6 months, depending upon the efficiency of the pre-treatment system. If the pre-treatment system is really good, The cleaning requirement is sometimes even once in a year. But if the quality, if the efficiency of pretreatment system and effectiveness is less, some of the plants are cleaning once in 10 days, once in 15 days also. So efficiency of operation and of RO system and the longevity of the membrane life depends on the efficiency of your pretreatment system, because when you do more CIP, then membranes try to become lesser salt rejections takes place, and because of that salt passage increases to the membrane, salinity level increases, so you are forced to replace the membrane. So life of the membranes comes down if the pretreatment efficiency is low. This is a typical spiral wound membrane sectional view. You can see this membrane has a polyamide layer. This is the effective layer which has the pore size of 0.001 microns and which rejects the monovalent, divalent, and trivalent ions. There is a polysulfone layer and the polyester base layer, which are supporting layers to give strength to this polyamide layer. So this is a typical membrane sheet. This sheet of membrane is used and rolled as a spiral wound to make spiral wound membranes. This is a typical reverse osmosis membrane. You can see the raw water enters from one end and leaves it at the other end. While it is passing through, these are the sheets. You can see the brown color sheets are the membrane sheets. In between, they are glued together. The two sheets are glued together as a pouch, and it has got a spacer, that is a permeate spacer in between for the water to get collected and flow gradually to the center pipe and get collected. So multiple pouches of permeate multiple pouches of RO membranes uh, are glued together and rolled as a membrane sheet here in the spiral form. That is the reason why it is called spiral wound membranes. You can see this is the permeate tube. The yellow line is a permeate tube which collects the permeate that is collected in the pouches of the membranes, and then it is passed to the next one. In generally, the membranes are arranged, 6 or 7 membranes arranged in one pressure vessel, and uh, the feed water, when it flows from this end to other end, because of part of the low TDS water getting separated and collected in the permeate tube, the concentration of water continuously increases. So from the first membrane to second membrane, when it enters the feed water, the salinity increases. So when it reaches the last membrane, it reaches the maximum salinity, and permeate in one tube and another tube is connected and interconnected through small interconnecting pieces, and it is collected to the at the end of the RO pressure vessels, and it is collected in a header. So this is a typical arrangement. You can see in this one is a membrane sheet. This is the sheet which is perforate. This is one like a channel. This is a permeate channel spacer which is given here, and it is like a mesh which is there. And this is a brine channel where the brine water, feed water, when it passes through this and enables the water to flow from one end to the other end. This is the typical seawater reverse osmosis plant. It is a 100 ml Nimili desalination plant view is shown here. The other process in brackish water technology is electrodialysis process. This is the process that is used in the dialysis system also. This is the electrochemical separation process in which the ions are transferred through ion exchange membranes by means of direct current. This is DC current is involved in this. The process uses electrical driving force to transfer positively charged ion from the source of water to the cathode and negatively charged ion to the anodes. So when you have both positive and negative charge ions are separated, the water that is going through is free from ions. So because of it, its salinity level goes down. So you can see here, the cathode is here, the anode is here. So negatively charged ions are collected here, positively charged ions are collected here. So the water finally flowing through carries no ions. So because of it, the solute, the salinity level is low. But during the operation, when it goes for a longer period, the concentration of positive ions increases and negative ions increases, and the efficiency starts dropping. So this is the time at which you need to recharge it, or you have to do the um, process reversal in case of electrodialysis process, in order to remove these uh, ions that are collected in the anodes and cathodes. So in the reversal dialysis process is a advancement over the electrodialysis process. But there, instead of using a flushing cycle to remove it, you use a reversal of electrodes in order to reject the collected positive and negative charge ions, and then they form a brine and it is removed and rejected. How do we increase the availability and reliability in the SWRO plants? Because this is very important in order to improve the availability and reliability. What we do is selection of proper seawater intake location, because seawater intake assumes importance because the pretreatment system is decided based on the quality of seawater. So first you have to do an extensive survey of seawater in that area to locate the intake location. Also you have to do the bathymetry, you have to do the lithology of that area, also the variation in the water quality, especially if it is very closer to the river discharges and other things, the variation in TSS and algae carryover, many things have to be looked into. So a study of seawater quality is very important, and the various other aspects which I told is very important in deciding the location of the intake. And also intake location important because it also decides the price. If the location, if the water is very shallow, you have to go a deep intake system which is very far away from shore. For example, for a 100 mld plant, you need a depth of around at least 10 meters. For example, in Nimili Desalination Plant, the seawater intake pipe is 1 kilometer from the shore, and the intake mouth is just kept 1 kilometer from the shore level. And because of that, the pipeline also has to be laid throughout the length, and that increases the cost because laying of pipeline requires dredging, and any operation that is into the sea is costlier when compared to the operation which is similar operation that is carried out in the land. So seawater intake location carries very important, and if the quality of seawater is very good, your pre-treatment system becomes very simple, and your operation of the plant also is becomes easier. Extensive survey has to be done in order to assess the seawater quality which is used for the plant design. Designing the plant with suitable pre-treatment system to supply the RO train with consistent feed water quality, meeting the membrane manufacturer's requirement. For example, membrane manufacturers specify heavy metals should not be present, and the SDI of the water reaching in the feed water should be in the range of around 3 to 4. SDI is 3 to 4 for 15 minutes. Then this turbidity should be in the range of less than 0.5 NTU. So they specify certain conditions, and you have to meet all those conditions by designing a proper suitable pre-treatment system. If the feed water quality is bad, your pre-treatment system should needs to be more extensive and expensive also, and it also consumes a lot of chemicals. So choosing a right intake location will simplify the pretreatment process and consumption, reduce the consumption of chemicals. Choosing proven equipments and proven membranes also increases the availability and reliability of the plant. Providing standby equipments enable the plant operation during the maintenance of the equipments, and this increases, having a standby equipment increases the availability of the plant. And choosing the material of construction of the equipment, tanks and piping to avoid corrosion is also an important factor. For example, high pressure pipings and brine pipings are nowadays are made with the super duplex stainless steel. All low pressure pipings are made up, low pressure piping, low pressure equipment are made up of non-metals, especially like FRP, PVC, CPVC, or HDPE are used generally. Adopting right welding procedure for high pressure pump is very much essential, because improper welding process and the heat treatment process results in crevice and pitting corrosion in the high pressure piping. And when the corrosion starts, it requires frequent shutdown for attending to the pipes. So to increase the reliability, the specifically all the pipings have to be properly properly welded and treated. And predictive and preventive maintenance, another important factor which also increases the reliability and availability of the plant. Where does India stand in desalination when compared to the global desalination? International Desalination Association reveals that as per their assessment in 2015, 18,426 desalination plants are there, which are producing 86.8 million cubic meter per day, which has almost increased by 30% in by 2020. And the Global Water Intelligence estimates the global water desalination market value is 13.31 billion US dollars in 2016. World desalination market, you can see that the light color is almost the installed capacities, and this one, and the dark colored are the predicted order positions in that zone up to 2016. You can see Saudi Arabia is leading in that, and where India is leading. But India has taken a leap now by going in for more desalination plants. Chennai is almost acting like a Detroit of desalination, and it has got already 2 into 100 mld plants. One more 150 mld desalination plant is already coming up in Nimili plant, and another 400 mld plant tender documents are under preparation, and it will be shortly released. So if this is ready, the Nimili Desal in Chennai alone will have 750,000 meter cube per day desalination plants, and which will totally take care of the water scarcity even during the summer if the rains fail. You can see that this is the various installed capacities and different zones or different countries. Saudi Arabia leads it, and its installed capacity is close to around 8.5 million meter cube per day, and other countries are trying to catch up. UAE has also added a lot of capacity in recent times. This figure shows the increase in membrane desalination, which is indicated by means of a red line, compared to the blue line, which is thermal desalination plants, because of the standalone cost of a desalination plant of seawater reverse osmosis process is much lower than thermal process. It started gaining because of its importance of easy startup, shutdown. There are a lot of other advantages which has given more momentum for the membrane desalination plants to grow. This slide shows the maroon line with the seawater reverse osmosis plants which are installed, and blue is the brackish water plants installed. The brackish water plants are limited because it depends on the charging capacity of the aquifers. Second, the inland plants should have an area for brine disposal. Since in reverse osmosis seawater plants, they are close to the coastal region, the brine can be easily disposed to the sea. Whereas in brackish water desalination plant, they are mostly inland plants, and the disposal of brine becomes a big challenge. So in many of the big plants, in Saudi Arabia, there are big plants in Salbug and Boyab, which is around 60,000 meter cube per day capacity. They have built big evaporation ponds, which is around 1.5 kilometers by 2 kilometers in dimension, to evaporate the brine and dispose it. This shows the comparison of a thermal versus membrane process. You can see it is in GCC countries on the right side extreme. The contribution to thermal plant is much more when compared to the other areas. It is because the earlier plants which are erected in Middle East were all thermal desalination plants, and later additions in the recent time is due to membrane desalination. And you can see that in globally it is only 5%, whereas GCC countries it is still 11% is there. So the blue segment indicates the thermal process, and the maroon segment indicates the membrane process. Indian desalination plant market forecast and opportunities in 2019 predicted that the growth rate will be around 19% and it will increase further. As per the statistics in 2017, India had around 500 desalination plants. When I say desalination plant, it is of considerable capacity, like close to more than 1,000 meter cube per day capacity. They are operating in different parts of the country. But recently, there are a lot of developments. Even the Gujarat and Maharashtra are trying to bring in more desalination plants. Some desalination plant talks are going on the east coast of Tamil Nadu, as well as in the Andhra state also. Organization like WebAx's role in desalination. What do we expect from such organization? One is continuous R&D efforts are to be made in order to reduce the capital cost and of the plant, and also design optimization to be done in order to bring down the operation cost. Reduce the energy consumption of the process by going in for more advanced energy recovery processes, and using VFD plus low pressure membranes to reduce the energy consumption. Minimize the other operating costs in order to reduce the lifetime water cost. Extend the desalination plant life so that the add-on expenses on life extensions can be reduced. Incorporate innovative technologies that reduces the lifetime water cost of the plant and make it more competitive, and develop technologies for the byproduct that has value additions. By doing all these things, we can make desalination still more attractive. WABAC believes in desalination as an alternative and reliable, feasible, sustainable source of water. WABAC is able to offer optimized, tailor-made solution for both the production of drinking water as well as industrial applications, using saline water as the source, or in case of industries, we are using even the effluent from the industries for generating the feed water requirement of the plant. Backed by in-house R&D centers in Austria, India, and Switzerland, a lot of developments had been made in WABAC. Cooperation with universities and development partners goes a long way with WABAC quest for innovations. future desalination technologies which are under development. I have tried to explain only few. There are a lot of developments are going on. The more important one which are gaining momentum is listed in this presentation. Forward osmosis process, membrane distillation process, captive deionization process, humidification, dehumidification process, solar desalination, and new RO membrane developments which are promising. Regarding osmosis and reverse osmosis, I explained earlier. The osmosis is nothing but the forward osmosis, and reverse osmosis is applied force which is in the more than the osmotic pressure in order to have the water molecules separated. So the normal osmotic process is the forward osmosis process, which is under development. This uses a semi-permeable membrane to separate salt from the water, similar to RO process. Forward osmosis uses the osmotic pressure gradient instead of hydraulic pressure gradient, which is used in RO, to create the driving force for the water transport through the membranes. So I explained very clearly, in RO process we raise the pressure to around 55 to 70 bar depending upon the salinity of the water to push the water molecule through the pores. Whereas in forward osmosis process, the hydraulic gradient between the two fluids on either side of the membrane acts as the driving force for separating the pure water. Energy required is very less to drive the water flux, because the driving force is the different in gradients in the salinity levels. Forward osmosis is an innovative membrane-based technology, and it has got potential to reduce the cost and environmental impacts of desalination. There's a lot of research is going on in this process. There are plants which have been built to a capacity of 100 to 200 meter cube per day, and they are running successfully, and research is continuing in this forward osmosis process. You can see that this is the real heart of the system, which is the forward osmosis system. Saline water is sent through one end and collected on the other end as a brine, and there is a draw solution which has got high concentration when compared to this saline water. Because of the difference in salinity difference, pure water molecules try to pass through the membrane and get into the draw solution to dilute it. This diluted draw solution is taken through a tank, and there is a separation process where the pure water is separated from the draw solution and it is collected separately, and the draw solution is circulated back. So the important aspect in this forward osmosis is, one is draw solution, another one is a membranes, which can have the draw solution is very important because it should not use any toxic or anything, so that this toxic carryover from this into the pure water can affect the downstream process or usage. Another thing is the membrane it has to be developed so that it's more matured, and it can operate for a longer hours without much of a problem, much fouling, all those things. So this process is still under development, and yes, it has got a lot of potential in concentrating the water, and this is suitable for application with high concentration water also, because you can see RO process has a limitation up to 50 to 55,000 ppm, whereas this process can use high salinity water also. And there is one process called osmotic assisted process, in which they go up to 250,000 meter cube, 250,000 ppm of water, and concentrating it to before the evaporation process to form salt. Membrane distillation process. It combines the membrane technology with the evaporation process in a single unit. The appeal of the MD process is that it requires less pressure, closer to only 1.5 or 2 bar, and relatively lesser feed temperature in the range of 70 to 90 degrees centigrade. Because for to increasing the thermal efficiency, the people have gone in for a top drain temperature of 130 degrees, 110 to 130 degrees. So the scaling potential increases when the recovery increases in the thermal processes. Whereas in MD processes, they are able to use the waste heat or solar heat in order to generate the temperature in the seawater, and then we can do desalination in the MD. The transport water vapor through the pores of the membrane, which is generally hydrophobic in nature, and using the temperature difference across the membrane. That is actually one end the hot water is allowed to pass through the membrane, so the vapor passes through the pores in the hydrophobic membranes of the MD process and reaches the other side where it is cooled and condensed. The vapor generation increases with more temperature difference, and the membrane allows water vapor to penetrate the hydrophobic surface and repels the liquid. The clean vapor is carried away in the membrane and it is condensed as a pure water. The carriers can be air, it can be also uh, other process by which the carrier of vapor can be taken into the area where it is condensed and water can be obtained from there. This is the typical membrane distillation process, which this membrane is a hydrophobic membrane, because of which only vapors will pass through. You can see the green arrows, which is the vapor passing through, and the water is rejected. So when the hot water passes through in the process, the vapor goes in, and here on the other side there is a cold water flowing. Because of that, this surface is cold and the vapor is condensed in this, and then it is collected. So it can be air gap can be used, it can be water vapor can be it can be vacuum can be used in order to generate more amount of vapor. The next process is capacitive deionization process. This process is a low pressure process. It is a non-membrane desalination technology. It uses electrostatic forces to remove the dissolved ions from the solution. The saline water is passed through a pair of electrodes which has a potential difference of around 1.2 volts. So when compared to ED process, you can see that the voltage applied is much lower in this process of CD. The electrodes consists of a porous carbon aerogel which has a very high specific surface area. So this is very important in case of CD. The specific surface area should be more, and it has to have very low electrical resistivity. Ions are absorbed on the electrodes of opposing charges in batching process. This is a batching process in which the feed water is allowed to pass through, and the positive and the negative ions are collected on the respective electrodes, and when the water passes through, leaving alone all the ions, the low salinity water is collected. But after a process time, the batch ends, and the electrodes are saturated with the ions, and then when the electrical potential is totally removed and fresh water is allowed to, that seawater is allowed to pass through, it flushes out the ions which are collected in the positive electrode and negative electrode, because there is no charge now, and it is removed as a brine. So it is a batch process. For example, it operates for 1 hour, then 5 minutes it has to be flushed, then 1 hour, and then 5 minutes flushing is to be take place. And this has got a very good effect with respect to low salinity water with the brackish water with the silica and other things, because electrodes are not affected by this silica. To generate CD, the applied potential is removed and the ions attached to the electrodes are released and flushed out of the system. Flushing of cell using a small quantity of product water generates a concentrated stream, which is a stream which is called brine. Unlike ion exchange process, no additional chemicals are required for regeneration of the electrosorbent in this system. Humidification, dehumidification process. This mimics a natural water cycle to desalinate the water. Natural water cycle is nothing but seawater getting evaporated, carried out, and then it is cooled, and then rain falls, and the rain comes back through rivers and goes back into the sea. This is the natural cycle, and this humidification, dehumidification process mimics that process. Seawater is first converted into vapor by evaporation in dry air, and the dry air carries uh, the water vapor into the next segment. This water vapor is then condensed from the air in a condenser to produce fresh water. So where the evaporation takes place in the dry air, it is called humidification, and where the condensation takes place, it is dehumidification. Normal atmospheric air is used as the medium to carry the vapor that is generated in the fresh water into fresh water, seawater into fresh water. That is, heat for evaporation can be obtained from various sources, including solar, thermal, geothermal, and a combination of all these three. This is a simple schematic diagram of a humidification dehumidification process. Dry air is allowed to pass through a solar collector where uh, it is heat is applied to it, and to the and seawater is evaporated, and the evaporated seawater along with the vapor goes down, and the vapor is carried and passed on to the dehumidification chamber, where cold water is passed through to condense that water, and the condensate leaves out and the air also comes out. So it is a dry air which carries the vapor and condenses at the dehumidifier and then sent out. So it's a simple process. Only thing advantage of this system is it can use waste heat as well as solar heat in generation of water. And this is also in development and in many of the research laboratories. Solar dome desalination is another attractive desalination that is coming up. It uses concentrated solar energy by strategically arranging the banks of mirror, and that will speed up the natural process of evaporation within the dome, which is a greenhouse structure. The seawater flows into the dome by means of a gravity, and it is it enters the glass aqueduct in the dome, where the solar reflections from the various mirrors concentrate and heats this and then generates the vapor. The dense steam produced falls onto as a tropical rainstorm within the dome as clean and pure water. This water is then collected and piped to the reservoir, and this process is under development, and they are saying that the water produced is much cheaper because it uses solar energy, but the capital cost for installation is quite high. Solar desalination with the solar power. Saudi Arabia is building a solar desalination plant in its east coast. It will be using concentrated photovoltaic cell in order to produce electricity, and that electricity will be used in a reverse osmosis plant to produce water. See, Marubani has recently bid for 0.0157 per kilowatt hour for a 800 megawatt photovoltaic plant in Qatar, which means the in Indian equivalent it is 1.13 rupees per kilowatt hour. In Nimili Desalination Plant, if you take, it's a seawater reverse osmosis plant of 100 ml capacity. The electricity contributes to 70% of the plant O&M cost. And in Tamil Nadu, the electricity cost is around 6.35 rupees per kilowatt hour. Assumed if the power cost goes down from 6.35 to 1.13, that means there is a reduction of 82% in the power cost, and how attractive the water cost will be. So only the limitation will be there needs to be a breakthrough in the electricity storage, because the solar electricity is produced during the daytime. The effective period will be around 6 to 7 hours. So remaining period, this electricity stored should be used. So there should be a breakthrough in this storage capacity at a very low cost. Promising new membrane developments. Nano engineered membranes, carbon nanotube membranes, and Aquaporin membranes are under development. The development is aiming at getting a very high flux, at least 25 to 30% more flux than the existing membranes with the same applied pressure. So that means it will reduce the production cost because the flux is increased through the membranes with the same applied pressure. Aquaporin membranes are nothing but it's a mimic of natural root which absorb water from the soil. The required water for the plant is obtained through roots, and the roots absorb the water from the soil. Same thing is mimicked in this aquaporin membranes, and these three membranes are under development and in advanced stages. And I think within another 2-3 years, maybe commercial models will be coming out in the market. Factors influencing the desalinated water cost. One is plant size. When the size of the plant becomes bigger, the economy, the efficiency of the equipment used is very high. For example, in a small capacity plant, if the efficiency of a pump is 70 to 75%, in high capacity plants, we get efficiency in the range of 80 to 85 to 88%. So that makes lesser specific pump consumption. Another thing, economy of size is always there to bring down the cost per meter cube of the plant constructed. Feed water salinity and quality. The higher the salinity of feed water, the more the pressure is required for conversion of a recovery of water from the seawater. And also the recovery is restricted. When the salinity is high, the recovery is restricted to for example 40 to 42%, whereas when the salinity level is in the range of 32,000 ppm, it can go up to 50-55% recovery also. So for the same capacity, same installed capacity, the cost of the plant will be much lesser. Also the quality of the water. For example, if you need a potable water quality of 500 ppm, the cost of the plant will be much lesser when compared to going in for a potable water quality of 100 ppm. So the quality of potable water or the end product also decides the cost of the plant. Product water quality. See, product water quality is what we discuss, and in feed water quality, when the quality of feed water is bad, you have to go in for an elaborate pretreatment system in order to make the quality of water suitable for RO application. So feed water quality also decides the cost of the plant. Bathymetry and lithology of seabed. See, when the bathymetry decides that the sea is very shallow, then you have to go in for a long intake pipes to go for a required depth. Lithology decides whether it is boulders are there or what is the route of the pipeline to be selected. And when more boulders are there or rocks are there, then the cost of excavation increases and the cost of installation of intake itself goes high. So selecting of intake may also depend upon the bathymetry and lithology of the seabed. Energy cost. Um, Energy cost forms, I told, 70% of the O&M, operating and maintenance cost of a seawater reverse osmosis plant. So when the energy cost goes down, automatically the end product cost, that is potable water cost, goes down. Plant location and infrastructure. Plant location decides for a seawater reverse osmosis plant of around 100 mld capacity, we will require around 15 acres of land. If this 15 acres of land is to be located in a urban area, the cost of the plot itself will be very high. So you have to move away from the city. Then you can go for a cheaper land cost, and also the infrastructure required also decide. But when you move it away from the city, you have to build a pipeline in order to bring the water back to the city and distribute it. So you have to have you have to decide between which is optimum, like having the plant how very far away from the city, or in the midway between the city and the cheap location of land. Then the process types. There are various pre-treatment processes available, which you have to choose based on the seawater quality, which decides the price of the price of the plant, and which also has an implication in the final water quality and its price. Plant equipment specifications. For example, we can go in for a plant with a life of 10 years with the cheaper equipments with the lesser sophisticated material of construction. For example, instead of going in for super duplex stainless steel, you can go for duplex stainless steel, or even a steel which is much lesser in cost, but gives only a lesser life. So this decides about the life of the plant as well as the cost of the plant. So most of the modern plants are aiming at a life of around 25 to 30 years, and they go in for super duplex stainless steel for high pressure applications, valves and pumps, and for low pressure application they go in for non-metallic pipes like high density polyethylene, GRP or FRP, so on. And the low pressure pumps of low capacities and chemical cleaning system, they go in for fiberglass type pumps or PP pumps. So by choosing suitable specification for the materials, the cost can be optimized as well as the life of the plant can be also improved by avoiding corrosion. Then the financial cost is also plays a role in the price of water that is produced. There are certain myths about a desalination plant which I wanted to clarify here. The most important is desalination affects the marine life. The main concern is that the brine is discharged into the sea, and due to its high salt concentration, it can affect the marine life. In case of thermal plants, there is also a slight amount of thermal heat that is from the condenser when the hot water is discharged. Around 3-4 degrees centigrade more than the seawater temperature, the water is discharged into the sea, and that also gives a concern to the environmentalist. Actually, modern plants discharges are let deep in the modern plants. It is let deep into the sea through special diffuser arrangements in such a way that discharge is diluted in a radius of around 30 to 40 meters from the diffuser point. After dilution, the salinity difference between the brine discharge and the seawater is less than 5% in most of the plants. Environmental agencies are having a constant watch on this water discharges, and there is a requirement that the plants have to collect samples in certain zones which are specified by the environmental agencies, and they have to test it with a third party laboratory and send the reports to them for their further renewals. And in case of thermal plants, what they do, they mix the brine discharge along with the condenser water and the other waters which are discharged in that area. In some of the plants, they are even discharging where sewage is treated, sewage is discharged. The rejected water is mixed with this sewage discharge and sent to the sea in order to dilute it even before admitting into the sea. Then proper diffuser system can bring down the temperature and the less than 1 degree centigrade. So there is technology available currently to alleviate this concern that desalination will affect the marine life. In countries like Australia, they are doing some lab tests to collect the brine water and the organisms which are living in that zone, and make them to survive in the lab for 6 months period with the same water specification, to prove that this water quality does not, the discharge water quality from the outfall does not affect the marine life. So it has been proven in some of the um, uh, plants in Australia. This is one, maybe some of the tender requirement which call for the stringent requirements. The second myth is that desalinated water cost is very high. In the last 30 years, several inventions in energy recovery devices have reduced the power consumption from 8.5 kilowatt hour per meter cube to 3.2 kilowatt hour per meter cube. Here I want to just bring to the knowledge that initial days when desalination plants, seawater reverse osmosis plants were built, we were not having energy recovery devices, and the recovery of the plant was only 30%. The modern plants have a recovery of around 47 to 50%. Because of that, the specific power consumption was in the range of 8.5 to even 9 kilowatt hour per meter cube, because 70% of the brine was discharged with a full pressure, and the energy was killed in the brine valve and then sent to the sea. Later, reverse running pumps were introduced in the brine in order to recover at least 50% of the brine energy. Then came with the development a Pelton wheel, which had energy recovery efficiency of around 80 to 85%. So that reduces the specific power consumption to 4.5 kilowatt hour per meter cube, and the recovery also simultaneously increased to 40%. There was a later development called hydro turbochargers, which were introduced, and they improve the efficiency further and reduce the specific power consumption to 4 to 4.2 kilowatt hour per meter cube. But modern development of DWER with uh, DWER and Energy Recovery Incorporated (ERI), the these energy recovery devices have an efficiency of 96 to 97%, and because of these energy recovery devices, the specific power consumption has come down close to 3 to 3.2 kilowatt hour per meter cube. Due to R&D efforts, the productivity of membrane has also increased considerably, and a lot of other research is going on if the new membranes come, and the flux is going to increase further. Mass production of RO membranes has also brought down the RO membranes price. See, initial days in 1980s and 86, we were buying membranes at a price of around $700 to $800, and this area available in the membrane was around 300 to 330 feet. Modern membranes are 440 to 400 feet square area, and the price has come down less than $400 per membrane. So the cost of the membrane is also brought down considerably due to the bulk productions. As I have already told, the international boot desalination plants of high capacities has brought down the water cost to 0.41 to 0.5 US dollar per meter cube. That is 1,000 liters cost only 0.41 to 0.5 US dollars, which was in the range of around $2.5 to $3.2 in 1980s. And boot water cost in Tamil Nadu is rupees 56 in ninth year, with the electricity cost of 6.35 per kilowatt hour. With solar power cost drastically falling, the desalinated water cost is bound to drop further. R&D efforts on a new membrane discussed earlier are in full swing to bring down the specific power consumption and increase productivity further. The myth about desalination, one more thing is desalinated water does not have minerals and not good for health. Many people are confused seawater desalination with the house RO units. See, the house RO units take feed water from either well or municipal water, where the TDS is much lower, and the RO membranes reject approximately 90% of the salt from it. Because of that, the salt level available in the kitchen RO units are much lower. Whereas seawater reverse osmosis plant, it can be designed for any required quality. Generally, the municipal SWRO plants are designed to meet WHO as well, and that is World Health Organization and ISO standards 10,500 in India. They produce water with total dissolved solids in the range of 250 to 500 milligrams per liter and contains all minerals, whatever it is in the seawater. It is calcium, magnesium, sodium, potassium, and carbonates, bicarbonates, everything that is available in seawater in little concentration it is available. So whatever minerals required for the body are provided by this potable water generated from seawater reverse osmosis plant. The water that is produced in the thermal desalination plant is of very high quality. That is the TDS level, the total dissolved solid is in the range of 5 to 10 milligrams per liter. So in such plants, you have to go in for remineralization to increase the level of minerals, that is especially the calcium, and also improve the LSI, that is longilinear saturation index, is made positive, so that when this water flows through the pipe, there is no corrosion in the pipes. As I told already, the water produced in desalination plant can also be remineralized to boost the calcium level, fluoride level, or also increase the taste. Desalination is a failure and the plant will not be reliable. This is also a myth that is existing not in the Middle East or Western region. In India, some people have that notion, which is not true. The whole of the Middle East countries, utility water demand is successfully met with desalinated water over decades. The availability of desalination plant is as high as 97%, making them more reliable. SWRO plants can be started in short time and also can be stopped when required. So they can be operated need based. Expertise available in India to build and operate the desalination plant with companies like Wabag. So there is totally a wrong myth that desalination plant is a failure, because in the Middle East there are plants which are operating more than 35 years, and also they have gone in for a life extension to increase the life to another 10 years. So the desalination plant are going to stay here
and they are the need of the hour in order to have a reliable and feasible water supply at cheap rates. Industries can source water, that is the raw water required for producing desalination, from different sources. The raw water for desalination can be sourced from either sea, it can be from process effluents of its own industry, or it can collect water from municipal waste and then desalinate it and reuse it, as in the case of tertiary treatment plants. And it can also use brackish water or backwaters in order to produce desalinated water for the industries. In Gujarat, there are many plants coming up which are going to use the backwaters. Reliance has successfully commissioned the plants which are using its own effluent in order to produce the desalinated water required for the industry. Beach wells on the shore can also be supply filtered water required for the desalination. Only thing, it needs clearance from the environmental agencies. From any type of raw water provided, desalinated water can be designed and produced with the TDS varying between 5 milligrams per liter to whatever TDS, whatever that is required. For inland plants, evaporation ponds can solve the brine disposal issues. I would like to conclude stating that desalination is an attractive solution and it gives a reliable and effective way of handling the scarcity of water with a reasonable price. However, the order of preference in which the water can be obtained is the cheapest source is natural water, precipitation, or rainwater, which is collected and used. Second is domestic wastewater can also be effectively treated and used for producing either industrial water, which can substitute the water which is being supplied, and the water which is used by industries, fresh water which is used by industry, can be diverted for drinking application. The domestic wastewater treatment and generation of water is widely, generation of utility water is widely used in countries like Australia, Singapore, where it is indirect potabilization is done. Indirect potabilization means the domestic wastewater is treated and then it is mixed with the stored water, that is the lake water, and then the lake water is further treated before distributing into the city domestic water or utility water. There are some countries where direct potabilization is also being used, and in fact WABAG has also designed and supplied one such plant, and it is successfully operating. That is, domestic wastewater is treated and directly supplied to the taps. This is the second source available, second cheapest source. The third cheapest source is industrial wastewater, which is available as a waste in the industries, can be recycled by treatment in a reverse osmosis process, and the water generated to the required quality by the industry, and it can be reused. So this is the third source. The fourth one comes the desalinated water. So desalinated water definitely can substitute the requirement of water wherever there is a shortage or scarcity is there. I thank you, and I'm ready for any question answer session.
Thank you, Amir, for a wonderful presentation and covering the topic. I think in the given time frame, whatever best possible you could share, and that you have shared. And let me tell you that we've received a lot of questions, and some of them have been sent to you over your phone. So I request you to kindly take up as many as possible. And for all those, if your answers, your queries are not answered during this presentation and this program, please don't worry, because we will be getting back to you through your through the email response. Right, Amir?
Yeah, okay. I will go
Yeah.
ahead with questions one by one. I'll read the question and give the answer.
Yes. Yes,
Uh,
and in case we are not able to take up all the questions, because we have, due to paucity of time, we will be getting back to them through the email replies. Right, Amir? We'll do that as well.
Right. Okay.
Yeah,
Right.
yeah,
Starting. What is the production
yeah.
cost using seawater reverse osmosis process? See, I have told in my presentation also, the production cost for a seawater reverse osmosis plant of capacity range 50,000 meter cube per day, 50 mld to 100 mld, will be in the range of around, including the capital depreciation cost and the O&M cost, it is going to be around 47 to 48 rupees. And the plant which is running already, which is selling boot water, is charging around 56 rupees per 1000 liters in the 9th year of operation. See, in the year of operation, when it increases, the price may increase in the boot plant. So this is the one which is in India. I am telling this is the price. Whereas international prices already I have given, the lowest price is $0.41 per 1000 liters. Second question is, how much cost need for 1 liter of seawater desalination treatment? For a big high capacity plant, I told that in Middle East it is now 3 paise per liter, and in India it will be in the range of 5 paise per liter. Third question is whether there is requirement of post treatment process in seawater reverse osmosis technology. Yes, because seawater reverse osmosis permeate that is produced will have LSI negative, which is when sent through the steel pipes, it can result in corrosion. So generally the pH will be in the range of 6.5 to 6.8 depending upon the feed pH. So you have to remineralize it. Generally calcium and CO2 is added to increase the solubility of lime or pick up in calcium, and by the calcium addition you can increase the pH to 8.2 to 8.5, and also LSI make it positive, and then this is meets the requirement of ISO as well as WHO standard. Can these membranes be clarified during maintenance, or it has to be eventually replaced upon decrease in pressure? See, membranes, how we call it decrease in deterioration in performance is two things. One, the flow will come down, that is the permeate production will come down, or the salinity of water that is coming out will go higher. In this process, the chemically cleaning the membranes, you can get back the flux that is into the membranes, as well as the production can be regained by doing a CIP, that is cleaning in place process. We call it as a high pH cleaning and low pH cleaning is done for this. But when the salt rejection decreases, that is more salt passes through the membrane, this cannot be reverted because it deals with the pore size. Olden days we had a membrane called DuPont membranes, where we used to do PTA and PTB treatment and bring back the salt rejection in the membranes. But the modern spiral wound membranes does not have that process. Have the successful plants also utilize the value of byproducts to bring down the cost to $1 per meter cube as described by you? No, the water industry is specialized in its water treatment alone, but it has brought down the cost to $0.41 per meter cube
and in India it is maybe 0.7 dollar per meter cube. And so far we have not used the byproducts, but there is easier means. Actually, if the brine is taken to salt pans, the time that is required for salt to be produced can be halved, because the salinity of the water when compared to seawater is double. So it can be done, but the only thing is, since land is adequately available in the coastal region, so people are able to get water free of charge, the seawater, and they are able to produce salt. So that eliminates the pumping cost or land area that is required in the near the seawater desalination plants, which are very expensive. And because of that, people do not prefer to use the brine from the seawater reverse osmosis plant to produce salt. But definitely there are some process where mineral harvesting and special some salt solution preparations are possible as a byproduct from the brine that is generated in the seawater reverse osmosis process. How to reduce the impact of brine in ocean? I have explained it very clearly here. By means of a brine diffusers, properly you can design the diffuser to take the brine piping deeper into the sea, far away from the coast. For example, in Nimili plant, we have the diffusers located 500 meters from the shore at a depth of around 6.5 meters, and the diffusers recirculate the sea water in that zone and dilutes the water within 30-meter radius. And we have measured the salinity variation between the brine at a 30-meter point and the sea water is only 3%, and it is not affecting any brine life, any marine life in that area. In India, how much it will be effective for industries? It is very much effective, because many of the industries have started using the effluents, and they are using tertiary treatment RO, that is a brackish water RO, in order to produce the water that is in-house water requirement completely. So it is very effective. Reliance is leading it, and in many of the areas, Reliance industry has installed their own backwaters reverse osmosis plant and TTRO plants, that is tertiary treated RO plants, in order to produce the water, meet their water requirements. Is there any low cost solution for remote communities where laying pipes and maintaining a fixed plant is not feasible? Yes, actually solar desalination is the solution, because from the solar desalination you can have power produced at no cost, and this power can be used to run RO plant, and you can produce water out of it. Because seawater reverse osmosis or brackish water RO plants can be made modular in size, and it can be smaller. We can have even a plant of 5-meter cube per day capacity or 100-meter cube per day capacity for a community. And this study was done in Europe for African countries, and I think they are implementing it in many places. To address, next question is, to address preventive and predictive maintenance of motorized valves in desal system, what are basic criteria considered for valve maintenance, which are required salient features of actuators used to operate the valves in desalination plant? The main thing is in desalination plants, the valve should open and close when you require. So the actuators should be designed to open and close, especially in case of ultrafiltration system, quick opening and quick closing valves. So they are pneumatically actuated valves. Whereas in other places, it can be electrically actuated valves. But the function of the valve is fulfilled only when it has a closed shutoff and complete opening to reduce the pressure drop in the system. Closed shutoff is achieved by either torque limit switch with proper torque setting, and we have found that with the proper torque setting, we are able to have a tight shut-off and then proper closures. In desalination plants, when you design and install the valve and actuators, don't install valves and actuators below handholds, below the header openings, or the places where when you open the water will fall down, and this causes damage to the actuators. Even the solenoids of these actuators, if you have to locate the valves in such locations, relocate the solenoids away from it so that it is not affected by means of a seawater that is dropping, because seawater is corrosive when you open, and if it falls into the valve body and the parts, especially when the actuator body is aluminum, it results in a bad corrosion. You may have to go in for body replacement, that is actuator body replacement within 3-4 years of operation. So you need to be careful in locating it. The main maintenance what we have seen is sometimes when the keyways get slightly enlarged, or you have the keyway, the key itself slightly gets compressed. Because of that, the opening and closing is not full, and we have to go in for EN8 this one keys in order to have a high strength in it. And another problem what we are facing in the seawater reverse osmosis is the parts which are made up of super duplex stainless steel sometimes gets corroded because of improper heat treatment in the post foundry process, and that annealing process, if it is not done properly, there will be a precipitation taking place in the material, carbide precipitations, which results in galvanic cells and galvanic corrosion. So you need to be very careful in using the right material and the right treatment in the valves to have a longer life in valves. What are specific MOC required contact surfaces in desalination plant? See, main thing is high pressure piping, that is high pressure feed piping and brine piping. All these things are made up of super duplex stainless steel, where we call PREN number, PREN number more than 43 is being used in order to reduce the corrosion. The second thing is pumps, high pressure pumps, and low pressure pumps of high capacity are not available in non-metals. So you have to go for metallic pumps. If you go for metallic pumps handling seawater, you have to necessarily go in for super duplex stainless steel pumps. Similarly, valves in the high pressure line has to be super duplex, and valves in the low pressure line can be coated valves like nylon coated discs, and rubber lined valves can be used. And low pressure pipings, I found that HDPE piping is very handy, because repairing laying is difficult. It is not difficult because pinching of the stones and other thing does not cause puncture, and repairing also is not that difficult. And in Nimili plant, we have the entire plant made up of high density polyethylene piping. The low pressure piping entirely is high density polyethylene piping, and intake pipe and brine pipe are also high density polyethylene piping. And we have operated for nearly 7 years, and very less maintenance is required. What is the life cycle period of single unit SWRO spiral load membranes? The design life specified by the membrane manufacturer is 5 years, but whereas I have operated the plants and obtained a life of around 8 years in the membranes. And there are if the pre-treatment system is good, your CIP cleaning chemical cleaning frequencies are much lower, and because of that the deterioration in performance of membrane is very low, and you can extend the life of the membranes to 8 years. But at the same time, there are some plants where The membranes have been replaced once in 6 months, because every third day they used to clean the membranes, because the pre-treatment was not able to meet the requirements of the RO plants. So both the extremes are possible. If your pre-treatment is good, you are sensible in operating the plant, you can extend the life of the membrane to even 8 years. You need not replace the membranes for first 2 years. From third year onwards, you have to replace the membranes. Maybe one membrane per vessel. Out of 7 elements, one element which forms 14.28% replacement is sufficient. Maybe at the end of 6th year or 7th year, you may have to go in for 28% replacement to achieve the results. Results in the sense required salinity as well as required flow. Where is the WebAx R&D center in India? In India, we have in Chennai, and also we have association with the universities in order to do our research programs, and also we carry out the research projects in the sites also. Like for example, membrane distillation project we have done, ultrafiltration ceramic membranes we have done research on it, and so we are using different types of membranes and checking the performance. So different process research associated things are site associated research is being done in India, whereas in Switzerland and Austria, we are doing research with respect to micro pollutants removal and other things also. Excuse me, I'll take it. There is once again same question, whether there is a requirement of post-treatment process in SWRO technology. If it is for industrial application, no. If it is for domestic as well as utility application, yes. We would like to know the recent advancement in the technology and MOC for valves. MOC for valves is super duplex stainless steel is the advanced one, which many of the manufacturers are now able to supply valves with the super duplex stainless steel. The cost of 0.5 to $1 per meter cube cited by you, is it for saline water or brackish water? It is for seawater, even with a TDS close to 40,000 ppm. So it is the water cost I have told in Saudi Arabia. In eastern region of Saudi Arabia, in Arabian Sea, the salinity of water is around, the TDS is 45,000 ppm. And in the west coast, that is the Red Sea coast, the TDS level is around 41,000 ppm. So the water cost that I have mentioned, Jubail, is on the eastern region. And to reduce the cost of ownership and improve on the preventive maintenance capabilities, whether actuator technologies having inbuilt data logger features, two-wire network communications with PLC SCADA are mentioned in tender documents. Yes, tender documents deals in detail what is the type of technology that is used for and how they are to be connected to data logger, and some of the features which are there is this feedback system is very essential. For example, in UF system, if you see that when a backwash is to go on, or chemically enhanced cleaning is to go on, then there are sequencing, many valves are to be operated, and there is a sequence in it. So from one sequence to other sequence goes only when it the limit switch is operated, and the limit switch gives an indication to the process to continue that. And not only that, so since the valves are many in number, all these valves indications are very important to in the control room in order to know whether the system is functioning properly, or it is switching over to maintenance mode because of the valve fault. Because in an ultrafiltration system, if one valve is not operating, then the whole system has to switch over to the maintenance mode, so that the maintenance personnel can go and attend to it, whereas the remaining mode UF should operate, and then take the load of the entire system. Sir, who in the Indian government's nodal agency to propose, budget and approve the desalination projects in India? No, it is influenced by the individual states or the private owners, and they approach. Actually, for a desalination plant, environmental agencies are vital in clearing the coastal regulatory plants and inland plants. But maybe you may have to explore more, because my knowledge on this is very limited. Due to the growth of these kinds of technology, does the importance of inland water bodies laws is important? See, inland water bodies, the laws is important in the sense, because these are the areas through which you can get water at cheap rates. For example, if there is a river flowing, because of that, you can build a check dam and recharge the aquifer in that area, and you can draw water from the aquifer at a cheaper rates. Any other process which is done to convert the wastewater into drinking water or effluent water into an industrial water or a seawater is it involves process, power consumption, it also involves chemicals. So it is there is some cost involved in it. So the cheapest process is the natural water, and you have to conserve the natural water and enrich actually the soil in order to increase the groundwater level. Do we really need this kind of technology when we are
think, excuse me, Amir, I think
Yeah.
we won't be able to take more questions. It's already one. So as per the schedule time, we would like to close it now. So maybe this question, which you have already read, maybe we can take this one, and this can be the last one, please. Rest will take up over the email, please.
Okay. We really need this kind of technology when we are blessed with lots of water bodies. Yes, water bodies are there, but still these water bodies are not sufficient to meet the requirements in the urban areas. So we need some technologies which can supplement the available natural water that is available at a cheapest rate. So the more and more research has to be done to bring down the water cost. That is, we call as a lifetime water cost. That is the cost during the entire life of the plant. Average water cost is called lifetime water cost. So we need technologies to bring down the lifetime water cost. So more research is to go on. Yeah, are we closing it with this? There is one more small question.
Yes.
What is
Okay,
the
please,
56
please.
rupees?
Yeah,
56
please.
It is 56 rupees per cubic meter. Per cubic, 1 cubic meter is 1000 liters. So someone has asked what is the 56 rupees production cost. It is for 1000 rupees of 1000 liters of water produced. Okay, remaining questions we can pass it on in an email. I can respond to it.
Yeah, so thank you so much, Amir, for this presentation. As I said, wonderful, enriching, informative, and you have covered whatever best possible we could in this given time frame. And thank you so much for your presence and taking this forward, this entire program of 2 hours. And thank you so much, all the participants, for joining us for this event today. And I'm hopeful that you liked it. Also, I would like to share that we keep doing such events on regular basis. We do have a training program lined up on 19th also. So if you want to know anything more about these upcoming and planned events, so please you can write to us at info@thewaterdigest.com. Also, you can follow us on LinkedIn, Twitter, and many other Facebook handles. Thank you so much. Thank you so much, everyone. Thank you.